So for the linear acceleration, what we can do is, we'll just have a look through this. So speed is distance divided by time. Velocity is just distance with a direction divided by time, which is just displacement divided by time. Now if you have a car that's travelling at a constant speed, it's different than if it's travelling at if it's going around a corner. Its velocity is changing because its direction is changing. Now as soon as a velocity changes, you experience a force. That's why when you're going around the corner of a car, you feel a pull towards out away from the curve. Now for the constant uniform acceleration questions, these are all the quantities that you need and the units listed. So you've got time, acceleration, u, which is the initial velocity, v, which is final velocity, and s, the displacement. So acceleration is linked to all forces. You get negative acceleration, it's deceleration; positive, it'll be acceleration. So this topic is generally about particles which move in a straight line and accelerate uniformly. There's another topic later on which is about circular motion, and we'll be covering that in due course. There are constant uniform acceleration, speed time graphs, and problem solving involving two particles. These are the four equations that you can use, and you should have them taken down and looking at them. They're page 50 of the log tables. And if you fill out a table, you don't need this whole section here every time. It's probably just no harm to have it, just for demonstration purposes to show it. You mightn't even need this bit here then either. So the next bit then is that if you have this example, so if I have a runner here, his acceleration is 2.3 meters per second if he starts from rest. So that's initial velocity be 0. In a time of 2 seconds, what will be the final velocity and the distance? You can pause this and just have a go at the question. I'm going to move on though, and this is another example that you could do. Just so you can pause it, I'll show the answers. Probably I'll put them on text file at the end. So you've got acceleration, a deceleration of minus 1.5 meters per second squared. You have an initial velocity and a final velocity, and you're asked to find the time and the distance. So I'm going to move on from this here as well. Just another example here. It's a plane, you know its initial velocity, you know its final velocity, you know the distance taken, and you're asked to work out the deceleration and the time. So again, pause, give the question a go. Now this is what I wanted to cover today, which is distance time graphs. Now distance time graph is straightforward like this here. You have on the x-axis you'd have time, and we always have time on the x-axis for these graphs. So time will always be on the x-axis here, and for this one we've got distance here. Now if you have a distance time graph, you can see a few different things. If the graph is like this, a straight line, the object is moving at a constant velocity, assuming that it's going in the one direction. We'll just assume that. In this case, when we have a distance time graph, when it's going up like this, what's happening is the further in this time you cover a very little distance, but if you go to the same amount of time, this from here to here, you'll see that it covers a good bit more distance. And if you were to go the same again from here to here, you can see that it's covered an even greater distance from there to there, from let's say this point here to this point, to that point. And I know this is kind of messy, but you get the idea of it, from there to there. So what's happening is, after each time you're covering more distance. Now for a distance time graph, when this is the case, this shows that the object is accelerating. Now we have another one, so have a little think about this. If I go to, let's say, the first lot of time there, it's covered a massive distance. It's gone from this point here all the way to this point here. It's covered a great distance. But if I go again here, you can see over this time interval it's only covered from there to there. So you can assume that when a distance time graph is like this, we have deceleration. Probably only one L deceleration. Sure. Okay. Now they're distance time graphs. They're handy enough, but normally when we're doing these, there's a better way to look at things. Now, distance time graphs would have been used in junior cert. For the leaving cert, we look at velocity time graphs. So that instead of distance, we have velocity here, and time is still on this axis. And there's a trick you can do with velocity time graphs. Now, when this is happening, what you got is the velocity is increasing with time. So this is for accelerating. Now, if I go this one here, you see an object is accelerating first section, traveling at a constant velocity, and then decelerating. Now this is probably a question you could have a quick go of, which makes use of this. So you've got a car, travels along a straight road, it passes point 3 p at the speed of 12 meters per second and accelerates uniformly for 6 seconds to a total speed of 30 meters per second. We'll give a go with that question in a second. I'm just going to go back to this here. The main reason why we use velocity time graphs is that there's something about them, that if we know the area underneath this graph, so to do that we'd have two triangles, this triangle here, so it's a half the base by the perpendicular height, this triangle here, and then this rectangle which would just be the base by the height, and this would be the half the base by the perpendicular height as well. If you work out these three areas and add them together, the total area under the curve in a velocity time graph is the same as a distance travelled. So I'll just put that there. That's why we use velocity time graphs. It's really the main reason, that if you can draw out this properly, it's a very quick way to work out the distance travelled. It's a lot quicker than using the formula. For this you'd have to use S is equal to UT plus 1/2 AT squared for this section. You'd have to use it for this section here to get the displacement in that section, and you'd also have to use, because this is constant velocity, so those four equations don't work, so you'd have to use distance is equal to speed multiplied by time for that section. So if you're to do it mathematically, it takes a lot longer. If you understand the velocity time graphs and the area under the velocity time graphs is equal to the displacement covered, it's a lot quicker than using these formulas here. So the question I'd like you to try, and so the idea would be to pause it here, give the question a go, and then I'll put up the solution thereafter. Okay, so for the solution, now this is coming from the exam papers. Wherever you see an F, it's the same as acceleration. This is just in the old log tables and the old solutions. So this is the first part of it there. Second part, that's the formula you'd use there. The third part is that. The other way. Okay. Now, there's one small thing we might as well just show here. So if you have velocity time graphs and you've got a curve like this, this would mean that the acceleration is not constant, that the accelerating is accelerating. And likewise with that one. The area between the graph and the time axis represents the distance travelled. The slope of the graph represents the acceleration. If a particle starts from rest, then velocity is equal to a times t. That's just a simplification of v is equal to u plus at. If it starts from rest, that's equal to 0. And if a particle accelerates from rest for a time t1, acceleration a immediately decelerates to rest, and in time t2, the deceleration then would be in the same ratio as the first time to the second time, the deceleration to the acceleration. That's if it accelerates to rest and then decelerates to rest. That's the important thing about that one there. Okay, so that's it. I'll keep. I don't know if that worked. Stop recording.